Yesterday, we introduced the idea of concavity. So we've already talked about the idea about direction. We know that the derivative, the sign of the derivative tells us about the direction of the function. That's summarized up here in this line. The sign of the derivative tells us about the direction of the function. If the derivative is positive, the function is increasing, the values are going up. If the derivative is 0 at a point, let's say, then the function is, it could happen on an interval. If the derivative is 0, then the function is flat. It's neither increasing nor decreasing. If the derivative is negative, then the function is decreasing. So the sign of the derivative tells us about the direction of the function. Yesterday, we introduced the idea of a second derivative. That's just the derivative of the derivative. The same thing applies. The sign of the derivative tells us about the direction of the function, but everything's going up one derivative. So the sign of the second derivative tells us about the direction of the first derivative. So if the second derivative is positive, then the first derivative is increasing. If the second derivative is negative, then the first derivative is decreasing. If we add a third derivative, that would tell us about the direction of the second derivative, and so on. But the sign of the second derivative tells us about the direction of the first derivative. Those two things tell us about something about the concavity of the function. And the concavity of the function is how the function is bent. So the concavity is how the function is bent. So if the first derivative is increasing, we say that the function is concave up. So the concave part is facing up if the first derivative is positive. This is because the slope is increasing. The values of the slope is increasing. So we also drew 4 things that could happen. 4 combinations. Increasing in concave up, decreasing in concave up, increasing in concave down, decreasing in concave down. So we've got 2 choices for direction, 2 choices for concavity. That makes 4 choices total. So here on this first row, I've got 2 increasing functions. And on the second row, I've got 2 decreasing functions. So here we have on this row increasing, and on this row decreasing. In that first column, I have 2 functions that are concave up. So this first column is concave up, and the second column is concave down. So those are the 4 things that could happen. Two choices for direction, 2 choices for concavity, 4 things total. There is one that we kind of left off where f prime is flat. If f prime is flat, then the function is neither concave up nor concave down. Neither concave up nor concave down means instead of being bent, the function will just be going straight. So there's no concavity. So I guess we could have on the other, in this other column, no concavity. We have another word for no concavity. We can see that the graph is not bent at all. So our other word for no concavity would just be linear. Linear functions don't have any concavity. When something is bent, the convex part is what we decided to frame our vision with, probably because of the positive negative business. So notice that in these concave up, the concave part of the function is going up. So the concave part of the function is facing up. So concave up means the water comes back up at you. So when you put the spoon in the sink concave up, that will guarantee that it is directly under the faucet, so that when you turn the faucet on, you get sprayed with the water. Does everybody know what I'm talking about? If you don't know what I'm talking about, you need to take some responsibility at home and maybe do the dishes once in a while. So they're like, oh, I don't know what you're talking about. I put the dishes in the sink and then magically they're clean. I don't know what's going on. Take some responsibility and do the dishes. So we decided to frame that we decided to frame this in terms of concavity. So the concave part is up, so the spoon is up in the sink. The water goes up when it hits you. Concave down means you put the spoon face down in the sink. We all know that if you don't put it directly on the sink floor itself, then it'll bounce and flip over because the spoon is trying to get you when you turn the water on. Any questions? We want to read concave up and concave down as a slope increasing and a slope decreasing. So the reason we want to think of it in terms of slope increasing versus slope decreasing rather than getting steeper or getting less steep. What's the opposite of steeper? Is it just less steep? Flatter? I don't know. That's not a good description either. We want to think of the slope increasing versus the slope decreasing. The reason is that we have a function can be increasing or decreasing. Now, if we look at the slope of a tangent line here on concave up, notice that the slope on this first point is going to be less than the slope later on. The slope is increasing. The slope at that first point is less than the slope at the second point. The same thing is happening on the decreasing concave up function. The value is going to be less, but since they're both negative, it's less negative. So down here, this is pretty steep, but it's steep and negative. And then later on, it's less negative. Less negative is more. That's increasing. We increase to get to less negative. A lot of times I'm going to be lazy and I'm going to say steeper, but what I mean is less negative. That's what we mean by increasing slope. So this slope here is like -2, and this slope here is -1/2. That is less negative. That is an increase. So concave up is increasing slope. Concave down is decreasing slope. And the same thing happens. So here, at this first point, we can see that the slope is like 3, and then later on, the slope is less. So when things are positive, that makes sense, right? It's less steep, so it's less slope. But when things are negative, decreasing is going to be more negative. So up here, we've got this relatively mild slope, say -1/2, and then later on, we've got this much steeper slope, but it is more negative. So if here the slope is -1/2, then later on the slope is -2. That is a decrease in the slope. From -1/2, it went down to -2. Problem is, steepness doesn't have a direction. We just say it's steep going up or steep going down. So it's not a good description when we're talking about concavity. Any questions? How's everybody okay? A point where a function is changing concavity is called an inflection point. A point where a function is changing concavity is called an inflection point. We might not be changing direction, but we're changing concavity. F changes direction at a local maximum or a local minimum. F changes concavity at inflection points. We don't have words for the two kinds of inflection points when we go from concave up to concave down, or from concave down to concave up. We don't have words for those two different ones. We just call them both inflection points. Just changing concavity. F changes direction at a local maximum or a local minimum. We have two different kinds of change in direction. A local maximum, where we go from increasing to decreasing, or a local minimum, where we go from decreasing to increasing. The first derivative is going to be telling us about direction. The second derivative is going to tell us about inflection or concavity. So the changes in direction, finding local maximum values or local minimum values, or locations of local maximums or local minimums, we will be appealing to the first derivative. To find these, we're going to solve f prime equals 0 and then figure out what's going on at those points. To find inflection points, we're going to solve f double prime equals 0 and find out what's going on there. So our first derivative game, we're going to be solving f prime equals 0 and then doing some stuff. For inflection points, we're going to solve f double prime equals 0. Any questions? How's everybody okay? Everything's all very sad. You all look like this. Because second derivative is so simple. Yeah, we got it. Wait, is there a quiz today? No? Then yeah, we got it. It's fine. In California, we're not going to have snow days, not in the Bay Area. We're going to have smoke days. It's kind of frightening. Anybody know what a snow day is? I don't know if you're familiar. The snow day is like in places where it snows. Sometimes it's like snows so much, like it's not safe to be coming to school, so they declare a snow day. And like you take this, just like yesterday, it's like they schools canceled today. Too dangerous to go out and go to school. So in California, we're just doing that now, but it's smoke. Kids will be all celebrating. Yeah, it's smoke day. Let's go out and play in the ashes of our burning civilization. So if you recall, I'm just going to use this function again because we're familiar with what it looks like. So we already know where there's a local maximum when x is -1. There's a local minimum when x is equal to 3. So we know those points. We got that from taking the first derivative. F prime of x was going to be x squared minus 2x minus 3. Our second derivative is 2x minus 2. If we want to find the inflection points of our function, we'll look for where the second derivative is equal to 0. Now, this is not going to guarantee that we have inflection points at these locations. These are just possible locations. We have to check if the function is actually changing concavity. So we take the second derivative, set it equal to 0, and solve. Not necessarily going to be an inflection point at 1. In this case, we know that there is because we know what the function looks like. Or from your side, we know what the function looks like. Concave down, and then later on there's a minimum, so it must be concave up. So it must be changing. Now we know where it's changing, but we have to check. This is where there might be an inflection point. This is a possible inflection point. We need to check if the function changes concavity. We need to check that the function is actually changing concavity. There's only one possible inflection point. That's where f double prime is equal to 0. So we're only dividing the number line into 2 intervals, before 1 and after 1. So we're going to pick some values to plug in before 1, pick some values to plug in after 1, and check the sign of the second derivative. So f double prime, we need to pick something before 1. I like 0. That's my favorite thing to plug in. Make my 0 look different, so it's not this 0 that I'm plugging in, but this 0 over here. So just by checking one value from the interval before 1, we get the concavity of all the values before 1, or we get the sign of the second derivative for all values before 1. So that means that f is going to be concave down. Then I need to pick something after 1. I'll pick 10 because it's easy to plug in. So we plug in 10, we get 20 minus 2, which is 18. So after 1, f double prime is positive, and that means the function is concave up. So we see that the function did change concavity at 0, so we have an inflection point at 0. Sorry, 1. In this case, we knew that going in because we know what this function looks like because I've been using it for the past 3 days. I used it yesterday too. Y'all just didn't see me using this function yesterday. It was very important. I can't tell you what I was doing. It was top secret. So we know what the function looks like. We know that there's a local maximum at -1 and a local minimum later on at 3. That means it was concave down at that local maximum, concave up at that local minimum. So it must be changing somewhere. And by solving second derivative equals 0, we found out where it's changing. Inflection points are sometimes harder to spot. So if we look at rats. If we look at our function, there we go. We know that the function is changing concavity when x is equal to 1. Our first derivative was x squared minus 2x minus 3. The zeros of our, oops. Sorry, those of you playing at home, I did not switch. There we go. Yeah. First, I typed that in, and then I typed that one in, so it appears. So the zeros of our first derivative are telling us where the function is, has a critical point, where the function is changing, or possibly changing direction. In this case, we see that change in direction at -1, and we see another change in direction at 3. The first derivative is changing sign, so the function is changing direction. If we throw in addition to this, the second derivative, 2x minus 2, there's the 0 for the second derivative at 1. That's where the function is changing concavity. It's kind of hard to spot the function changing concavity, as the derivative is going from decreasing to increasing. If we look at the first derivative, the blue parabola, that's going to be a minimum. That's where the parabola is changing direction. That's where the first derivative is changing direction. So that's telling us that the function is changing concavity. Questions? How's everybody okay? Funny. Notice that in Calc 3, it's the same week and we're doing the same thing. In Calc 3, I am talking about the same shit. I'm just using more variables to do it. We have a function of 2 variables, and I say, well, where are the critical points? Take the derivative and set it equal to 0, the first derivative and set it equal to 0. But since there are 2 inputs, there are 2 first derivatives. And since there are 2 first derivatives, there are 4 second derivatives. We just have to figure out how to combine them, but we just take take the first derivative, set it equal to 0, and solve. But just instead of making it one equation with one variable, it makes two equations with two variables. So in Calc 3, in the future, when you take Calc 3, eventually you'll be doing the same thing that you did here in Calc 1. We just take off the restriction where it's difficult. We make our lives difficult by only allowing one variable. We make it easier to picture, harder to set up a problem. You know what I mean? It makes the mechanics of doing stuff easier. It makes it easier for us to picture because we only let one thing change. But then later on, especially in Calc 2, when we want to start modeling some situations, we've got to write everything in terms of one variable. And that's just like makes things much worse. But Calc 3 is like, oh, hey, let's just use more variables. The important thing to remember is that the thinking is the same. How is the function changing? That's the first derivative. What direction is the function going? Is it going up or going down? Or is it going flat? Then we just ask another derivative question. How is that change changing? Is it changing more or is it going to be changing less? Any questions? There's a new bunch of assignments that have been thrown your way. That sounds like I was trying to absolve myself of responsibility. I should take responsibility. There's a new bunch of problems that I threw your way, that I assigned to you. Just trying to duck out of the way. It's like, oh, these problems, they just showed up. I don't know what happened. I'm the fucker that put the problems in front of you. So I'll take responsibility for that. I gave you some more homework. Here's what that homework is based on. The problem starts off with how do we measure speed? And like the answer is like a speedometer. That'd be awesome. If I was going to write a calculus book, I would title a section, how do we measure speed? And then you would open it up, so like, oh, I wonder what's going on in chapter 2, section 1. It'd be like a speedometer. Chapter 2, section 2. And that would be it. But then it would never get published because the publishers would be like, oh, we need you to take this seriously. And I'm like, oh, I don't think I can do that. So here's one of the big things that we do. Because one of the things we have to remember that calculus is kind of a math class, but more importantly, it's an engineering class, right? This is like math, but we had to make a math class for engineers. I'm not looking down on engineers. I'm not looking, no, really, I'm not looking down. I'm just kidding. Like I said, engineers are way more useful than mathematicians. Which is really weird because in academics, like the Big Bang Theory was a terrible show. Yeah, I mean, if you like the Big Bang Theory, it's fine. I've admitted to liking the Fast and the Furious. It's like, that's like the greatest movie franchise of all time. But if you like the Big Bang Theory, you're wrong. It's a terrible show. And everybody in it is a terrible person. But they did nail one thing perfectly. They're like, Dr. Cooper, Dr. Hofstadter, Mr. Wolowitz. That's exactly how it is. You know what I mean? Like, I want, when you get your bachelor's degree, I want you to be proud, but I want you to remember that when you go to graduate school, you're still just an undergrad. You're just like, oh, you got your bachelor's degree. Ooh. Like, everybody in your family should be absolutely fucking stoked that you get your bachelor's degree. They should be absolutely fucking stoked when you get your associate's degree. But know that, like, all the academics are like, oh, you got your bachelor's degree. Ooh. Not me, because I only have a master's degree. And all the PhDs like, oh, Mr. Leach, how are you today? It's like, oh, fuck you. You know what I mean? Incidentally, I don't know if you plan on getting a PhD, but there's only one person that can be driving that. If you think you're going to get a PhD, no. If right now you're like, oh, maybe I'll get a PhD, you're not. Stop right now. Don't. If it's just like, oh, I think I'll do it. You get a PhD because you have to. Not anybody else telling you you have to, not for this particular job you have to, but there's something inside of you, and it's like, oh, I'm getting my PhD. You have to. There's something about something that you found as an undergrad, something that you found when you're working on a master's degree, if that's where you happen to stop, or that's where you happen to go after your bachelor's degree. There has to be something that hits you, and you have to get your PhD. You're like, oh no, I'm writing a dissertation on this topic, and I will find someone that will read that shit and confer upon me the degree of doctorate. If you're just like, oh, maybe I'll do this, that's not enough commitment. You can't just, that's not enough commitment for a dissertation. Do you know what I mean? You can get a bachelor's degree just because people are like, oh, you got to do this. And you're like, all right, 4 years of college and 6 years of college, 8 years of college. You get your bachelor's degree. You can sometimes even do a master's degree based on that. It's like, well, I don't know if I want to get a job yet, so I'm going to work at the school, get a master's degree. You can kind of get a master's, go through a master's degree that way. But once you get to PhD, it better come from you. It just has to. You know what I mean? Caveat, obviously, I'm not talking about everybody. Some people are going to be like so smart that they can just like do all this shit and they're like, ah, whatever. But I'm not talking about you. What were we talking about? Oh, yeah. So let's bring up our favorite framing where we decide a function. We define a function to be the position of some particle at time t. Sometimes we use very large particles like balls thrown into the air or cars hurtling down the road. But we define a function that represents a position at time t. The derivative with respect to time is how the position is changing over time. Change in position divided by change in time. Change in meters divided by change in seconds. This we call velocity. And then we take it one step further, and we take a second derivative. It's your change in your velocity. What is our change in velocity? Acceleration. That we call acceleration. Sample units, we might measure position at time t in meters. So your velocity will be meters per second, because that's how we build units of the derivative. We'll say meters per second. Your acceleration will be meters per second per second. So we summarize that with meters per second squared. Because we take the meters per second and divide that by seconds. Your change in velocity is measured in meters per second. Your change in time is seconds. So meters divided by seconds again, that's meters per second squared. And this is our favorite framing in Calc 1 for first and second derivative. So in the chapter 2 work, it opens up with how do we measure speed? Speed is change in position divided by change in time. Change in position divided by change in time is slope. Slope is derivative. All the same stuff. Any questions? Comments? Everybody's so sad today. You all look like this. It's because you missed out on a day of calculus, isn't it? Oh, stupid poor air quality. Missed out on a day of calculus. It's only going to be more days of poor air quality. So you're going to miss out on more days of calculus. I'm sure everybody was super disappointed that I didn't have time to pivot to doing the class online from home. I'm like, oh no, Leach, you can't do the class from home. That's so sad. Oh man, we're missing out so much. Fire up the Xbox. Oh man, what will I ever do? All right, so this is going to be our favorite framing device: position, velocity, acceleration. Position, velocity, acceleration. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing. I'll see you all on tomorrow, unless the air quality gets even worse.